Welcome to a variation of parameters example. So let's consider the equation we solved previously using reduction of order. Y double prime minus 3y prime plus 2y equals e to the 2x times cosine of 2x. And our job is to find the general solution. So again, just a quick note. We already solved this. With reduction of order. Now we'll do it again using variation of parameters. So when we do variation of parameters, the very first thing we should do is find the homogeneous general solution. So the first step is to find a fundamental set of solutions to the homogeneous equation. So we are looking at y double prime minus 3y prime plus 2y equals 0. So our characteristic equation we are working with r squared minus 3r plus 2 is equal to 0. And we have r minus 2 times r minus 1 is equal to 0. We therefore get r is equal to 1 or 2. And so we have y1 is e to the x, and y2 is e to the 2x. Next up, we assume that our y equals u1 times y1 plus u2 times y2 is a solution to the non-homogeneous equation. So to y double prime minus 3y prime plus 2y equals e to the 2x times cosine of 2x. So in this case, we are looking at y is equal to u1 times e to the x plus u2 times e to the 2x. Then we have the system y1 times u1 prime plus y2 times u2 prime equals 0. And y1 prime times u1 prime plus y2 prime times, u2 prime. That top equation should have been y1 u1 prime plus y2 u2 prime. And so second equation, we have y1 prime u1 prime plus y2 prime u2 prime is equal to f of x over p0 of x. So in our system, we had y1 was e to the x. So y1 prime is just e to the x. We had y2 was e to the 2x. So y2 prime is 2e to the 2x. Our f of x is the right-hand side of our equation. This is e to the 2x cosine of 2x. our p of 0, or p sub 0 of x. That's the coefficient in front of y double prime. In this case, that was just 1. So our system, we are looking at e to the x times u1 prime plus e to the 2x times u2 prime is equal to 0, is our first equation. And then we have e to the x times u1 prime plus 2e to the 2x times u2 prime is equal to e to the 2x cosine of 2x. So our next step is to solve the system. For u1 prime and u2 prime. So if we take our system, e to the x u1 prime plus e to the 2x times u2 prime equaling 0, and e to the x times u1 prime plus 2e to the 2x times u2 prime equals e to the 2x times cosine of 2x. I'm going to do this by running elimination. So if we subtract the bottom equation from the top, in this case, we wind up getting that our equations cancel out. Our e to the x u1 primes cancel, and e to the 2x minus 2 e to the 2x, we would have a negative e to the 2x times u2 prime is equal to negative e to the 2x cosine of 2x. And this gives us that u2 prime is equal to cosine of 2x. So in this step, we were eliminating u1 prime. In the next one, I'm going to go ahead and eliminate u2 prime. So if we do e to the x u1 prime plus e to the 2x u2 prime equals 0. And then here we had a e to the x u1 prime plus 2e to the 2x u2 prime equals e to the 2x cosine of 2x. If I go ahead and multiply the first equation by negative 2, we can eliminate u2 prime. So we have a negative 2 e to the x plus e to the x becomes a negative e to the x times u1 prime. We would have a negative e to the 2x plus a 2 e to the 2x cancels out our u2 prime term. And then on the right, negative 2 times 0 is just 0. We just have e to the 2x cosine of 2x. So here we wind up getting that u1 prime must equal a negative e to the x cosine 2x. So our next step is to solve for u1 and u2. So we know here we had that u1 prime was equal to, sorry, u2 prime. And we can do u1 prime. u1 prime is equal to negative e to the x cosine of 2x. And then we had u2 prime was simply equal to cosine of 2x. So if we integrate both of these, we get that u1 is just the integral of negative e to the x cosine of 2x dx. And we get that u2 is just the integral of cosine of 2x dx. So u2 we can quickly find. We just get 1/2 sine of 2x plus c2. For u1, we're going to need to do a little bit of integration by parts. So I'm going to rewrite this as negative integral e to the x cosine of 2x dx. If we do that integration, we have our u and dv. U is e to the x, dv is actually, let's swap that. Let's do cosine 2x as our u, and e to the x is our dv. So taking the derivative, we get -2 sine of 2x, and then -4 cosine of 2x. Integrating, we just have a bunch of e to the x's. So we add on the, or do a positive product, first diagonal, negative product, and then we do a positive integral. So we have integral of e to the x cosine of 2x dx is equal to e to the x cosine of 2x minus 2 e to the x sine of 2x minus 4 times the integral of e to the x cosine of 2x dx. So we have 5 times the integral of e to the x cosine of 2x dx is equal to e to the x cosine of 2x minus 2 e to the x sine of 2x. Therefore, we have the integral of e to the x cosine of 2x dx is equal to 1/5 e to the x cosine of 2x minus 2/5 e to the x sine of 2x. So we get that u1, which was negative integral of e to the x cosine of 2x dx, is equal to -1/5 e to the x cosine of 2x plus 2/5 e to the x sine of 2x. And then we would have a plus c1. Our last step is to find y. So we know that y is equal to u1 times y1 plus u2 times y2. So we have y is equal to, y1 was e to the x, I believe. Yes, y1 was e to the x and y2 was e to the 2x. So of e to the x times -1/5 e to the x cosine of 2x plus 2/5 e to the x sine of 2x plus c1. And then y2 was e to the 2x. And our we had 1/2 sine of 2x plus c2. So from here we have 1/2 sine of 2x plus c2. So if we sort of rearrange this and simplify, we get that y is equal to -1/5 e to the x, e to the 2x cosine of 2x. Then we have a 2/5 e to the 2x sine and a 1/2 e to the sine. That becomes plus 7/5 e to the 2x sine of 2x. Then we have plus C1 e to the x plus C2 e to the 2x. This looks slightly different, I think, than the original solution we got. I apologize if I made an algebraic error in either of them. We can have different versions of solutions simply because there are infinitely many particular solutions. Hopefully I did not make an algebraic error. If I did, this is at least the general process.